to see you. You're so close. How are you doing?
And you know Brian, right?
Yes, yes, yes.
Okay, I guess we're on. All right, it's a pleasure to welcome today Dr. Moulin, Pierre Moulin, from University of Illinois Urbana-Champaign. He's from the Electrical Engineering Department. He received his doctorate. What? Are we on or not?
Yes, we're on.
I see the Vista thing up there, which should be actually the interdisciplinary seminar series anyway. All right, I'll just go ahead and introduce him. So he received his doctoral degree from Washington University in St. Louis in 1990, and he subsequently joined the Belcour, right? Belcour Research Labs. And in 1996, he joined the University of Illinois at Urbana-Champaign, where he's currently professor of electrical engineering. He received numerous awards, and he's served on the editorial boards of information theory as well as image processing. He's the co-founding editor-in-chief, I think still editor-in-chief, right, of the Transaction and Information Forensics and Security. And he's on the board of governors for signal processing, and you name it, he's got it. And it's a pleasure to have you. Thank you for coming. The floor is yours.
Well, thank you for your kind introduction, and so hello to everyone. I guess the first thing should be to apologize for having Hong Kong Polytechnic. I knew I went east, but I didn't mean to go that far east. What happened is that I ran into a severe LaTeX problem on my computer, and I could not quite update the file the way I wanted it. So no disrespect meant, but what I really want to talk about is some of the very interesting applications of what I call discrete signaling. So this is a class of problems. In fact, there seem to be more and more applications where you want to communicate signals to a receiver or multiple receivers, but it has to be done in some discrete way. So there's no typo in the title. It's not discrete as opposed to analog. Okay, so it's really meant to be EET and not ETE. It's meant to be undetectable, or at least almost invisible, and we'll go over some of the applications. And these communication techniques actually are quite interesting. They give rise to some problems that are a bit different from standard signal processing or communication problems. And this notion of communicating discretely in a way that's invisible and so is, of course, not new. And from the title, I will in fact talk about some of the early applications of that 5,000 years ago. And all this has taken a new twist in the last 10 or 15 years due to problems like copyright protection, security, thank you, security of transmission, let's see if I can get this work, security of transmission and so on. And my plan today is to go over some of the applications. That's what I'm going to start with. And then once we have seen some of the driving applications, I'll introduce an information theoretic model to work with those problems. And I'll try to show that the underlying problems are fairly interesting. And then finally, I'll try to show how this theory has been put to practice. And it turns out there are significant difficulties making this theory practical. So I'll try to give some highlight about some of the difficulties that arise when you try to make this theory practical. So let's begin first with some overview, some applications. And roughly speaking, I would say talk about discrete signaling as being the fact as being the imperceptible embedding of data or messages into what's called covert data. And the covert data could be any kind of signal. It could be audio files, it could be video files, it could be software, it could be integrated circuits. and the embedding of this message should be done in a way that is not, say, visible. So if I have an image, I embed data in it, the result should be an image that looks really like the original. It should not be visible. If it's audio, you should not hear the difference after embedding data in a piece of music. Now, this message will then be sent to a receiver. And there are different functionalities, different applications. In some applications, we have what's called a private receiver that may share a cryptographic key, for instance, with the transmitter, or perhaps it could be a public key cryptographic system. So often these private receivers are used wherever you have a security requirement. In some applications, there's no security requirement, and you have what's called a public receiver. There's no key at all. Anyone can decode the data. So here will be some applications. For a public receiver, there's no security, no notion of security. And so an application could be, say, in-band captioning. Okay, so you have you're watching TV, and you imagine you're watching a movie, and it could be that you have different subtitles, okay, that are embedded in the movie. Some in Spanish, some in Chinese, and so on. And they're all embedded in the video, and you don't want them to be visible or audible unless no, the user basically selects the one that he or she wants to hear. Okay. Another big application would be annotation of databases. You imagine you have a large database of JPEG images, and you would like at some point to introduce a little descriptor of the pictures in the database. So there could be a little sound clip that describes what each image is about, or maybe a little piece of text, okay, that describes some information about the content of the picture or the context. And so one idea then is to basically have metadata. Okay, you're going to link the JPEGs to a little audio clip or to a little piece of text, but that may not be practical, or the database may really be a JPEG database. Then the alternative is to embed the video clip, the sound clip, or the text into the JPEG itself. And so a user then just downloads a JPEG, and then basically will just launch the appropriate program that plays out the audio clip or displays the text. But it will be embedded in the JPEG itself. So these are different ways where you may want to embed messages. There's no notion of security, really. It's meant for public consumption. And at the same time, the embedding of that information into the image should not damage or perturb the visual quality of the image. That's the sort of application. Can everyone read this well, or should we have the light turned off on the front row? We can't. Okay, so I will. Okay, I will not ask further then. Now let's talk about some of the other applications where there's more of a security requirement. So I call that a private receiver. And in fact, what started driving this field is digital rights management for multimedia. Okay, as basically music and video were distributed over public networks like the internet, came up all these issues of intellectual property right protection. Okay, and that gave rise to the idea, say, of watermarking. So by embedding a digital signature in a piece of music or video, it's like embedding a copyright notice, okay, into that file, and should be done in such a way that it cannot be removed, okay, unless you severely damage the file itself. It should not be some header that can be easily removed. It should be literally bound to the content, okay. So that's the idea of watermarking. So the applications. Actually, this is used nowadays, okay? When you go to the movie theater and you see a movie, it's watermarked, okay? And the idea is to protect against piracy. And so these techniques, they have been used actually to catch pirates. And who are the pirates? So one level is people who go to movie theater with a camcorder, and then they film the movie, and then they make a DVD and they sell it on the streets of Hong Kong, okay, for $1. So that's one way to do it, but it's very bad quality. The big concern of the movie industry is at an earlier level. So before the movie is even released to theaters, it is screened, okay, so by professionals, and journalists come over there. Already at that level, the movie can be stolen. I mean, the people who play the movie in these private theaters can be bribed. It has happened, and then so sometimes a pirated copy of the movie is released even before it has appeared in the theaters. Okay, so there was a famous example a few years ago where. By using watermarking, it was possible then to trace a pirated copy back to a private theater where the movie had been screened, and then they caught the culprit. Okay, so this was actually a man from Illinois, so he's, I guess, in jail now, and he has plenty of time to watch DVDs. Okay, and so this has actually been used to catch people who have done piracy. So when you go back home tonight and want to watch a movie, and make sure to think twice about it. Okay, is it pirated or not? So these are some applications in DRMs. Another big one is authentication. So that one is quite different. Okay, it's this. You see lots of pictures, and they can arise in, say, law enforcement applications. This can go to trial. Or this is a picture of O.J. Simpson that was actually used at his trial 12 years ago. And there's a whole debate with many pictures. Are these pictures real? Okay, so, well, yeah, they have been taken, certainly, but have they been doctored in some way? For instance, you know, when you look at the evidence from the scene, okay, has there been some tampering? Maybe some of the frames of the video have been edited or removed or something like this. In the case of the O.J. Simpson trial, there was a lot of debate at the trial whether the shoes that he was apparently wearing were the shoes that he was actually wearing. It was an important issue during the trial. So there are all sorts of pictures that have a lot of value, maybe for law enforcement reasons or for legal reasons, and you want to make really sure they have not been doctored in any way. Okay, and one way to do that is to embed some digital signature in such a way, if you design it properly, that if there has been some tampering, you can detect it. Okay, and maybe you can even say which part of the picture has been tampered with. Like, for instance, the shoes have been tampered with, something like this. So that's another application of discrete signaling. Okay, you embed a signature that's going to convey some information later about the kind of tampering that took place. So again, you see pictures like this, you really wonder whether they are real. Okay, so this policeman here in the streets of LA is trying to arrest this character that's dressed in a pretty funny way. So is this a forgery or was this a real picture? It turns out it was a real picture. Okay, it was a stage, but there's been no doctoring of that picture. So you see pictures, the ones that look fake may actually be real pictures. They have not been doctored, and vice versa. The one that looks real may have been doctored in some way. Another application of that, it's used in some states. I don't know about North Carolina, but in the state of Texas, watermarking is used in driver's licenses. Okay, so of course there are all these fake driver's licenses, and an easy way is to just scan the driver's license, and it's going to reveal some information. Okay, so visual inspection of a driver's license may not be enough to tell whether it's a legit one, but by embedding a watermark in the picture, in fact, with the proper scanner and the proper security, one can verify the authenticity of that picture. Okay? So there are many other applications. Okay, so content identification, what's called transaction tracking, where, say, if you think of video is processed at many stages by, say, maybe a television studio or whatnot, and at different levels of the processing, you may want to authenticate, okay, who has had access to the video and did what, and all this can be embedded in the video file itself. Okay? So these are all applications that have some notion of security, and you can take this notion of security to an even higher level, and this is the right column, by requiring the communication itself to be secret. In the sense, no one can know the communication is taking place. So it's not the same as, say, cryptography, where if I cryptographically cryptographically, if I encrypt my data, I send them, everyone can see I'm transmitting data. Moreover, it's obvious I'm trying to hide something because I've encrypted them. If you embed data in an image in a way that no one can notice, you can secretly communicate with someone, because if I send Hamid a picture, well, it's normal business, but no one may know that I'm in fact transmitting secret information. Okay, Hamid, please meet me for dinner at 8 p.m. Okay. So this kind of thing is truly secret communication, okay? And we'll go through some applications. And of course, people have wanted to do that for a very, very long time. But another big application of that is timing channels, okay? So timing channels are when you have, say, a network and you transmit packets. The timing of the packets can be used to convey information to receiver. So this is something that can be exploited by the sender to secretly send information, or exploited by an adversary to steal information from your computer without you even noticing it. Like your computer is sending out packets, but at the same time it leaks information about the computer in the form of encodings of the timings of the packets. So these are in fact two facets of the same issue, that there's a communication channel that no one sees. It's a subliminal channel, and it can be used to convey information. Okay. So this is what I really want to talk about in some detail now. Okay, it's called steganography. So it comes from ancient Greek, steganographo, okay, covert writing. And so you really want to hide the existence, the very existence of a hidden message. Who uses that? Well, anyone who wants to secretly communicate for good or for bad reasons. So
because it's written in Greek?
That's right, yes. But it was used actually before the Greeks. So the earliest applications of that are about 3,000 years ago, as far as I know, by the Chinese. So this has been used, we'll see the application, okay, but by military people, by spies, by revolutionaries, oppressed people who need to communicate, and then terrorists. Okay, it has been believed that terrorists have been using that as a way to secretly communicate over the internet, even though it hasn't been established really. Okay. So here's an application of that. Okay, so here's a letter that's written by a Chinese general to his emperor about 3,000 years ago on the eve of an important battle. And there's a secret message there. So if one reads the letter, it looks like a normal letter, but there's a hidden message that the general wanted to convey to his emperor. And the way you can decode the hidden message is by applying a secret mask. Okay, it's a very nice technique. There's a mask that both the sender and the receiver know. Just apply the mask onto the piece of paper I showed, and through the mask then you can read the secret message. Okay, so this is the secret message that you can read through the mask. So a few people laugh. Okay, so if you know Chinese, you can understand. If you don't know Chinese, here's the translation. So the secret message was Microsoft Windows crashed. Okay. So that's a good way to send hidden information, because if you look at that, you will not guess, no, this was the secret message. It really requires having this secret mask that only the receiver and the sender know. Okay? So it's a very nice technique. In fact, it has been analyzed mathematically. Okay, it's a very old technique, but it's a pretty good one. And nowadays, how would you do steganography? So if you want to hide information, say in images, how would you do? So an old favorite is what's called LSB embedding, LSB like least significant bit. It's very simple. You think of an image as a collection of n pixels. So each pixel value S1 as a number of values, say 256, okay, if it's an 8-bit grayscale image. So any number can be expanded in binary form with 8 bits. And the parity of this number here is determined by the least significant bit, which is in red here. So the idea is very simple. The least significant bit visually does not matter. Okay, I can replace the LSB of any picture of any pixel of a picture. To your eye, it would be the same quality. So why not just take a cover image like Lena and then replace the LSB with an information bit? So by doing so, you can transmit 1 bit of information per pixel, which is quite a bit. You could transmit a 256 kilobits of information with a standard image like Lena. Okay, it's pretty good. So it's a very obvious technique. It has been used a lot. Okay, and if you do that, we can look at the picture. This is Lena. Actually, they are subjected to the secret embedding. So the visual quality is really identical to the original, and yet it contains a lot of hidden information. If you look at the least significant bit plane before replacement, this is what it looks like. Okay, so it looks like a completely random bit plane. Okay, a random binary field with no apparent correlation. And the question, of course, is, well, maybe my eye cannot detect there's hidden information, but maybe a statistical analysis will reveal there's something hidden. You look at that and you say, well, anyway, when I took image processing, my professor told me that the LSB bits are pretty much uncorrelated and independent of the other bits. They are pretty much incompressible, okay? So statistically, it seems like this is going to fly. And in fact, it doesn't. No one who is careful would use that nowadays, because it turns out there are some slight correlations between, not only between adjacent pixels there, but also with higher bit planes. And there are very good universal tests that have been developed to identify the fact that unmistakably there's hidden information there. So if you use that kind of technique to secretly communicate, you'll be caught, okay? Because there are good techniques these days to do that, even though to your eye, it looked like a pretty good technique, okay? So in steganography, then the question is, well, what kind of code then should I come up with, okay? If this LSB embedding method, which was simple, does not work, what should I be using? Okay, so this is where the theory now is going to play a role. Okay, what kind of theory can we think of that will tell us whether such an embedding of information is detectable or not? Okay, so that's what leads me to part 2, and I'm going to look at a generic problem of hiding information in images. Okay. And so, for instance, here's a cover image. That's the Beckman Institute at the University of Illinois, where I work. So my office is here. And let's say I want to transmit some data. So I have a piece of text that can be represented by a sequence of about 2,000 bits. And I want to embed it in the picture. There may be a secret key. So I have an encoder that has 3 inputs: the cover image, the text I want to transmit, and the secret key. And that's, let's call it the watermarked image. Okay, it's the output of the encoder. And visually, it should look like the original. And indeed, it does. Okay, so the perceptual quality is very high. Okay, so if you look at that, you will not say there's anything hidden there. Now, if this was submitted directly to the decoder, so the decoder, with the help of the key, would then decode the text reliably. Okay, the code should be designed in such a way that the bits can be decoded without error. Now, what's really challenging in those applications is that you often have an adversary. Okay, when we're talking about digital rights management and so on, an adversary, knowing there is a watermark embedded there, will do its best to try to remove it. Okay, at the same time, they don't want to destroy the quality of the picture, because if it's a pirated movie, they could not resell it, right? So what they want to do is to take that watermarked image, maybe apply some degradation, okay, in the form of noise or something slightly different. And so this is what the pirate would do. Basically, there would be a channel controlled by an attacker, and the output of the channel should be perceptually close to the input. And at the same time, the degradation, the noise introduced by the channel would cause errors, okay, to the decoder. So that's the program of the attacker. Okay, it is to come up with to think of a channel with distortion constraints that's going to basically reduce the reliability of the decoding. And from the point of view of the sender and receiver, of course, they have the opposite goal. Okay, they want to come up with a code that's going to survive any kind of attack in a certain class, okay, or subject to distortion constraints, so that a certain level of reliability can be guaranteed. Okay? So if you think what are the requirements on such a system, I would say there are 4 of them. One is fidelity, and by fidelity we think here of embedding. Okay, after embedding, we should have a watermark image that's close to the original in some perceptual sense. Same with the attacker. The attacker does not want to introduce too much visual distortion. Another attribute of the system is payload. How many bits are you transmitting? Clearly, if I want to transmit more hidden bits, it's going to be harder. Okay, it's just a harder communication problem. Third one is the level of robustness you have against an attacker. In some problems, I may not have an attacker, so everything is great. Of course, I expect to transmit more bits reliably if I don't have noise in the system. If I have some noise in the system, there are different levels. It could be transmission noise, a Gaussian noise, or it could be noise that has been carefully designed by an adversary. And this is going to be much, much harder, as you can imagine, to guarantee a certain performance of communication in front of a extremely large class of possible attacks, okay, which could have arbitrary memory, for instance. And then the final attribute which you have in applications like steganography is detectability, okay? So do I want the fact that I'm communicating to be known or not, okay? So in the case of steganography, there's this constraint that the statistics of the watermarked signal should be identical or at least close to the statistics of the original, so that no statistical test can distinguish between the two. Okay, so that's a requirement that you have in some applications. So if we think communication concepts and block diagrams, we can sort of summarize what I said into a big block diagram here, where we have an encoder F, an encoding function F, with 3 inputs: the cover signal or the host S, the message we want to transmit M, and possibly this key here K. X is the marked signal or the marked image. Then the attacker subjects that X to a channel, okay, and the output is the degraded signal Y. And that channel could be fairly arbitrary. It does not need to be a memoryless channel in general. And then the decoder, having access to the degraded signal and the secret key, will try to produce an estimate M hat of the message that hopefully will be close with high probability to the original message M. Okay? So there are all sort of requirements, conditions. The attack channel is subject to distortion constraints, as we said. The encoding function is subject to distortion constraints as well. And if we look at that, there are different flavors of the problem. Okay, so for instance, in some problems, the receiver knows the host signal. That has got to be somewhat easier. Okay, if the receiver somehow knows the host signal, we could still use this model by allowing the key, the side information, to be correlated with the host. So if the receiver knows the host signal, we could say that K contains all of the information about S. So in other words, S is a function of K. So we'll not limit K to be just a cryptographic key that's independent of S. In general, in this model, we may allow for correlations between S and the side information K. And then, there's the issue of communication protocol. As soon as we talk about secret keys, it raises difficulties. Okay, it means that either you have a prior key exchange between sender and receiver, or you have, say, a public key cryptographic system. So these are important protocol issues. Again, the notion of security. Okay, if you have a system relying on keys, how about what happens if the keys are compromised? Okay, the reliability of your system could disappear. In fact, this is usually the case. And so these are basically some of the system issues that we need to be concerned with. Okay? So, and again, in terms of attacks, we can think in some cases no attack another level, just plain regular transmission noise, or maybe filtering some normal edits of signals that are commonly done in systems. And then when you have an adversary, it can go quite far. I mean, the adversary could try to do cryptanalysis to extract keys, could try to do what's called often surgical attacks to find the best possible attack with memory that basically makes reliable decoding impossible. So these are all aspects of the problem that, of course, make the problem more or less difficult. So let's talk about practical codes now. Okay, so these ideas have been around for a long time, and then in the 90s, people wanted to do DRM. Okay, they want to do watermark images or audio, protect them. So how do you do that? So the big methods that emerged in the 90s was based on spread spectrum, which looks like a very natural idea. Spread spectrum techniques have been designed to ensure reliable communication in presence of jammers. And we can think of the adversary as a jammer. And it's natural to borrow techniques from spread spectrum communications to do watermarking. So this is the way it's done. You have the whole signal, and you're going to add a secret pattern, okay, that's indexed by a secret key K. It's a cryptographic key. Also, the pattern depends on the message, okay? And so the way it's done is you have a normalized pattern, which is secret. It depends on the key. It depends on the message. Then the strength or the energy of this pattern will be modulated because you want to make sure that this pattern is not visible. So there will be some parameter alpha that can be controlled to ensure this fidelity constraint I was mentioning. And then you simply add this modulated pattern to the host and you transmit it. And visually or audibly, there's no difference between the host and the watermark signals. So very natural idea. Secrecy is ensured by using appropriate randomization here. In terms of communication performance, this works extremely well if the host S is known to the receiver. Basically, the receiver can then subtract S, and you enjoy all the advantages of, say, spread spectrum communication. So you can have very good reliability of communication, even though there's a jammer. Now, interestingly, if the host S is not known to the receiver, as is the case in fact in most applications, you look at that and basically you can think of S as being transmission noise. Okay, the information bearing signal is going from here, and then during the transmission it encounters this source of noise plus possibly noise introduced by the attacker. Now, unfortunately, the noise here is extremely large because it's a host signal. The energy is huge relative to the energy of the information-bearing signal. So that turns out to limit the performance of the decoder, and the performance of the decoder degrades dramatically as the power of the host signal gets larger. Okay, and because the power of the whole signal is typically much larger than that power here, the performance of these systems are usually pretty lousy. Okay? So then came the realization that in fact you can do much better because this host S should not be thought of as transmission noise, simply because it's known to the encoder. Okay? So if it is known to the encoder, it's known interference. It's a well-known problem in information theory. You can basically adapt in some optimal way to the presence of this interference and have much better codes than the spread spectrum codes. Okay? So the kind of codes that I use are called binning codes. So they have been around for a long time now in information theory. They appear in Slepp and Wolf's paper, in the Gelfand-Pinsker paper, in a paper by Costa. This is all 25 to 30 years ago. And so the rough idea, okay, I won't go into much detail, is to try to adapt optimally to this known interference. In fact, ideally, you would like to cancel out the interference. I mean, there are good communication techniques that manage to cancel out the interference prior to transmission. Now, you can't do that here because the interference is too powerful, and you have this fidelity requirement. Whatever you send has to be close to the original. So the thing you should shoot for is to adapt as best as you can to the interference. That would be the idea. and the context in which good, say, watermarking or data hiding or steganographic codes can be designed. Okay? So I want to give you a little bit of the flavor of these methods. They are very different from spread spectrum. And I will give a simple example here. Let's say I want to embed one bit in one feature, like a real valued feature of my signal. Okay, so maybe you can think of the features being maybe a sample of the signal, maybe in some transform domain, like some wavelet coefficient or some DCT coefficient. And the way I want to do that is by, so first of all, if we view the coefficients of the signal as following some distribution, maybe Gaussian or Laplacian distribution, the idea is to try to shape those distributions so that the receiver, okay, receiving a sample y, would see a distribution like this if bit 0 was transmitted, and would see this other distribution if bit 1 was transmitted. So these are basically modified version of the original distribution of the host. So the original distribution of the host, say, was extremely flat. Okay, imagine like a Gaussian with extremely large sigma. Okay, and so the transmitter basically shapes the PDF. And now, if you compare those two PDFs, okay, this is what the receiver gets under bit 0. This is what it gets under bit 1. You notice that the peaks here correspond to valleys here and vice versa. So statistically, you can distinguish between those two distributions. Okay, there is a, for instance, if you look at the Bhattacharya distance between these two distributions, it is quite significant. Okay, so then it seems like a good idea if you can do that, because if I want to embed one bit, I would take a collection of samples, and so each of those samples would convey information. And so the aggregate Bhattacharya distance would be basically n times the Bhattacharya distance for one sample. And so that's the sort of idea you want to play with. Okay, you say I want to shape my distributions, and you see that even if the sigma here was possibly even infinite, this trick may work, right? So the question is, how do you shape the distributions to achieve that effect? So if we look at the way I did it here, in the first case, you want to concentrate the distribution on, say, minus delta over 4 plus multiples of delta. For transmitting bit 1, I'm trying to concentrate the distribution around plus delta over 4, no, plus multiples of delta. So this actually can be done using quantization. Okay? So the encoder would be a very simple one. Let's call this quantization embedding. If this is the original host that follows this Gaussian distribution with large sigma, if I want to transmit bit 0, would use what looks like a quantization function. It's somewhat modified because the slope of the staircase here is positive. Okay, for a normal quantizer would have basically flat steps. Here they have a certain slope that is actually optimized. And so we have a certain quantization function that basically concentrates the output distribution of x around multiples of, say, delta over 4, 5 delta over 4, and so on. If I want to transmit bit 1, I have the same kind of quantizer, but it's offset from the first one, so that the distribution of x now concentrates around minus delta over 4 plus multiples of delta. Okay, that's a simple way in which you can achieve the concentration of the PDF that I want. Okay, so in terms of implementation, it's fairly easy. It does basically quantization. I won't go into detail why there's a certain slope here. The idea is, if you look at the line x is equal to s, basically, if you look at, say, mean squared error distortion, you have to look at the discrepancy between this dashed curve and the quantization function in a mean square sense. And that should be kept under control. That's the fidelity requirement. And by changing the slope, I can make the delta larger or smaller. I have control over that. So if I make delta larger, I spread out the reproduction code word, so it seems like a good idea. And so this alpha turns out to be a trade-off parameter that you can use to trade off distance between code words against robustness against noise. And I won't go into detail, but it's simply a trade-off parameter you can play with. Okay? So if we look fundamentally, okay, this is just to give the insight, okay, about how you could come up with a bidding code that is simple and that works well, even though the sigma of the host signal is large. If you go back to information theoretic limits now, we could ask questions like this. Well, you give me a communication system, and I would like to know what is the capacity. Okay, so what's the rate of information I can transmit per sample of the host? Okay, it's a natural question. In fact, if you remove all the side information, if you make the channel memoryless, this is Shannon's basic problem of communication. Okay, you have a channel and you want to compute the capacity for the channel. So what's more complicated here is that you do have side information. There are various distortion constraints, as I mentioned. And also, the channel here is not fixed. It's not even memoryless in general. It's a class of channels that satisfy a distortion constraint. So the way it's done is one defines a distortion function, which is here additive over the components. And then both the encoder and the attacker satisfy a certain distortion constraint. And with a tolerance level, say, let's call them D1 and D2. And there are different flavors of that. One is to require almost sure distortion constraints. Another one is to require expected distortion constraints. Both types of constraints can be handled in this framework. And so this analysis can be conducted. So you say, well, if I think capacity, I want to know what's the highest rate of transmission so that the error probability of the receiver will vanish as the length of the sequence goes to infinity. Okay, it's the classical setup for basically computing capacity. And you can ask other questions too. In many problems, capacity does not really matter. If I want to do authentication, you can think of it as only transmitting a few bits of information. In other words, you are trying to communicate at a rate that may be well below capacity. So capacity itself may not be the most useful metric. What you want to know is if my application requires me to communicate at rate R, I would like to know what's the error probability I'm going to get at rate R, okay, if I have a signal of length n. So that's extremely hard to compute, but the next best thing you could do is to compute what's called the reliability function for this data heading system, which basically looks at the error probability on a log scale. So you take the log and then you look at -1/n and you look at the limit of that. So it gives you the error exponent for the receiver. And the error exponent here, we have to look at the error exponent for the worst possible attack channel. And of course, you would like to come up with the best encoding and decoding function. Okay? And so that defines the reliability function. That's the best error exponent you could ever get for the best encoder and decoder. And of course, for practical encoder and decoder, you're going to have an error exponent that is worse than that. Okay? So it turns out this can be done too. Okay? So when looking at these data hiding problems, we have expression for capacity and not necessarily for reliability, but they are basically lower and upper bounds on the reliability functions that can be computed. They are random coding exponents or sphere packing exponents, and they can be calculated. Okay? So to give some insight in a distribution that's often encountered when we talk about signals, let's look at the case of Gaussian host. Okay, so if I think of the transform coefficients of an audio signal or an image, to a first approximation, I could say they are Gaussian and fairly independent. So if now we take this model, okay, we say the host consists of independent Gaussian random variables. The distortion constraints are mean square distortion constraints. Turns out you can compute everything. The results are really interesting. Okay, so if the host was known to the receiver, you're trying to communicate with a distortion level of D1. It's like the transmission power. the attack channel has noise level D2, let's say, and not surprisingly, the capacity is 1/2 log 1 plus D1 over D2, okay, famous formula. That's if the whole signal was known to the receiver. Now, what if it is not known to the receiver? So for the people in the 90s, they would say, well, this is huge noise, so maybe to my D2 here, which is the noise power, I should add the variance of the host, right? And therefore, the capacity would be much lower. But in fact, it's not true, okay? This is just one coding technique. If you compute the capacity for that scheme, you see remarkably that in the case where even the variance of the host is as large as you want, could even go to infinity, the capacity is the same as if the host was known to the receiver. So in other words, there's no penalty at all that is paid by the system for not knowing the host. Okay, so what looked like very large noise, it's in fact not noise. We can perfectly adapt to it in the sense of capacity. So this is analogous to this problem that Costa was working on in information theory back in the early 80s. Okay, and the data hiding problem actually, basically, it turns out to be a very important result for the data hiding problem. And so, moreover, you can compute the distributions that achieve capacity, and they're all Gaussian. Okay, so the distributions here that achieve capacity are obtained by scaling the host, adding a Gaussian, independent Gaussian information-bearing random variable, and then adding back here part of the scaled host signal, and that is the random variable x. And the worst possible channel that the attacker would use is actually a Gaussian channel. So that consists of additive white Gaussian noise followed by a scaling. Okay, so it turns out to be in fact, the Gaussian test channel from ray distortion theory. Now, just giving a broad overview of what kind of codes achieve capacity in practice. It turns out that these are, again, quantization schemes. I showed you a quantization scheme earlier. It was a scalar quantization scheme. It turns out that a general version of that uses lattice vector quantizer is capacity achieving if the dimension of the lattices is large enough, okay? And if you use random lattices. So the scheme would work like this, okay? You would take, just like in the scalar scheme, okay, you would take the host. It turns out you just scale it by some factor alpha. Then you have, say, the message here, and I'm showing here a two-stage encoder. We can ignore maybe the first stage. We want to embed a message M. We're going to select one of many cosets of a lattice, and we're going to do quantization of the signal here in the appropriate coset indexed by the message. So the result, U, to this result, will add back part of the host signal, 1 minus alpha times S, and that will be the mark signal. So the implementation of the encoder uses basically a lattice VQ. And then the mark signal here goes through this channel controlled by the attacker, and the signal Y received by the decoder, so the decoder is going to do this. It's going to decode Y in the union of all these cosets. So it's going to decode Y in the large lattice, and then it's going to find the closest, that means it's going to find the closest point, okay, in this large lattice closest to the received data. And then you look for that point, which of the cosets does it belong to, and that will be then the index of the message. Okay, that's the way the decoder works. It does quantization to a lattice, and then it outputs the index of the coset that this point belongs to. So that's the structure of the decoder. It's basically a lattice VQ decoder. And so that turns out, as I said, to achieve capacity. So these are very good schemes. Of course, it gives a lot of intuition, okay? How in practice should I do? You want basically good lattice VQ, okay, that have nice computational properties and at the same time have nearly spherical Voronoi cells and so on. So they're very good techniques from coding to try to do very well with this kind of communication scheme, okay, with guaranteed performance. So let me show a little bit in the time I have left how you would apply this to practice. I don't know how much time I should really spend to conclude this. But let me give a concrete example, okay? Okay, I would say take an image, and my goal would be to embed bits in that image, okay? So we have to think, what does capacity mean? So we take first a representation where the components are approximately independent. So let's say a block DCT transform, the way that's used in JPEG. Then you say, well, these coefficients are not quite ID because they have very different variances depending on frequency. Well, that's no big deal. There's a version of this problem that works with parallel Gaussian sources. Okay, so we can still derive capacity for that model. The Msc metric I was using may not be the best when you talk about images, but it can be extended to weighted Msc metrics. So you could have, say, frequency-weighted metrics, for instance. They're quite appropriate for problems like this. Then if you take an aggressive attacker, okay, the D2 by the attacker is 5 times the D1 by the embedder. You can compute capacity, okay, based on the statistics of the samples in all these channels. Capacity is about 0.01 bit per pixel, okay? So if this image has a 250,000 pixels, it means that maybe you can expect to send up to 2,500 bits of information. Now, of course, you have to be really, really careful when you make statements like this. Okay, capacity is an asymptotic notion, and there's you cannot say that you can even get nearly close to that. Okay, with a finite size image like we have here. Okay, but anyway, it gives you sort of a ballpark to shoot for. Okay, certainly you should not ever expect to transmit more than 2,500 bits of information. And so here's a scheme, one of the best schemes that that I know of. Okay, it was done by Madhav and Manjunath and their PhD student Solanki at UC Santa Barbara. So they, based on these DCT blocks, okay, they are going to look at what they call active blocks where there's enough energy. So that excludes, say, background blocks and so on. Within each active block, they're going to select 11 DCT coefficients. So that excludes the high frequencies, which are much less robust. An attacker could easily eliminate them. So they're not good for transmission presence of an adversary. The lower frequencies are too susceptible to distortion, so they end up choosing these middle frequencies instead. So the encoder that is used is actually takes the information bits in, does interleaving, we'll see why soon, and then uses a read Solomon code that is concatenated with the sort of quantization code I showed earlier, a scalar quantization code. And so if you look at the performance of their scheme, they, in this example, embed 14,000 bits of information. And so even if one may want to play a little bit around with the picture, all the bits are perfectly decoded. Okay, so they can be pretty nasty, do a lot of deletions and erasures, and the decoder, in everything they try, recovers every single bit of information, not a single error. So you look at that and you say, oh, this is 14,000 bits. It's more than the 2,500 just gave you. So what conclusion do we draw? Well, these are not the worst attacks. So to your eyes, they may look pretty nasty, but in terms of communication performance, they are not by far the most damaging. In simple Gaussian noise would be more damaging, okay? And so in fact, their coder, when I say it's one of the best ones I know, it will not resist Gaussian noise, okay? So it's one of the best ones I know in terms of resisting deletions and erasures, basically. So that's the kind of things you have to think about, okay? Some results can look very impressive, but you have to think, what class of attacks am I going to face? And just because you have good performance for one class of attacks doesn't guarantee good performance uniformly. The only way is to go back to basics, to the information theory, and say, I can prove, okay, that no matter what the attack is within a certain class, I'm going to be able to resist that if I have the right encoder. And the encoders I showed you have that property, and this one does not. Okay. I will not have much time. I'll just mention briefly that a big concern in practice is what is called geometric attacks. It's not just adding Gaussian noise or doing deletions or erasures. It is simple things like shifting a picture by, say, 1 pixel to the left or rotating it slightly. And so the decoder I've showed just before does not resist that kind of attack. It's viewed as a really big problem in practice. Yet, from an information theoretic point, it should not really matter, because if you have a channel where there's only a few additional unknown parameters, like the parameters of the geometric attack, like a translation or rotation parameter, in fact, capacity is the same. Okay, so fundamentally, it should not be an issue. The only problem is the practical codes that are designed. Okay, if they do not take this into account, they may not work at all. So it turns out that, so this is an even more drastic example. Okay, it's called warping. So you take this picture, imagine you have a fairly coarse grid here, and you apply a slightly different displacement to every grid point, and you do smooth interpolation between. So that's the result here. Okay, it's a smooth interpolated version. These are the worst possible attacks, as it turns out, because there's not only a few parameters, there could be many, many parameters. And then you take a loss in capacity. I mean, capacity is really lower than what it will be in the absence of these attacks. So there's a lot of work now, somewhere in our group, about constructing good bidding codes that can resist these kind of attacks. But it's really quite challenging. So we have codes now that can, say, resist extremely well these attacks. But these ones are still another beast. Okay, these, I believe, are the worst possible attacks. Let me just add briefly, okay, going back to steganography. So you would have the same issues of reliable decoding, but in addition, you will need to ensure that the statistics of the signal are preserved, okay, after embedding, which looks very difficult because a code introduces correlations. And so you would say, well, of course, the statistics after of the output of the code must be very different from the statistics of the input. And it's true. The only way to get around that is via randomization. And so we can prove that with the appropriate kind of randomization and under some assumptions on the source statistics, it is possible to have a family of codes that perfectly preserves the n-dimensional statistics, so guaranteed to be perfectly undetectable, and with essentially the same communication performance. Okay, so that's the kind of way steganography could be approached. So just to conclude, okay, I would say that in all these problems, for a long time people have tried things, see how they work, and then some creative attacker can break a scheme. Then you go back to square one and you try to improve the code. One other way to think about that is you state all of the possible assumptions and the things that an attacker could do. And then you try to see what are the fundamental performance limits of those systems. And the analysis then gives you optimal distributions as a byproduct. And then this actually can give you insight, can motivate you to develop codes now that have a distribution that basically is similar to these ideal distributions. And that is exactly what was done with these lattice VQ quantizers and what we're trying to do now with these more elaborate geometric attacks. Okay, it's a framework basically for trying to address some of those problems which seem to be quite important. Okay, and I think I'll conclude with that. Thank you.
Are there any questions? Yes, Brian.
It seems like the error probability in schemes like this would depend a lot on the key size.
Yes.
So what kinds of assumptions do you make about
the key size was huge, it was unbounded. So the in fact, the entropy of the key is in fact goes to infinity. Okay, it's not even a constant. Yes, because in fact our codes are randomly modulated codes. We're actually very inspired by your work, and it's basically these kind of codes that we use, and then the entropy of the key is huge. Yeah.
Has there been much work If you add a constraint on the key size?
We've not done that. So in practice, I guess one way is to select not fully randomized permutations, but to have some pseudo-random scheme basically for choosing permutations. But we have not looked at the performance of those schemes yet.
Any other questions?
Yes.
Go ahead.
Okay. If I want to transmit information in a in a picture, just hide my bits in the picture.
Yes.
If I have no distortion, no noise, can I hide as much information as I want?
Well, so if you say you have no distortion, so it means
just a very ideal concept.
you mean there's no attacker, you're saying?
No.
Okay. Well, if you have distortion for embedding, you're still limited, okay? I mean, in the extreme case where I require perfect fidelity, you're not even allowed to modify the image, so you can't transmit anything. So you're still limited, even if there's no attacker. You're still limited in your performance, and so in terms of the number of bits you can transmit, and the error probability. You need not have perfect decoding. I mean, there could be errors at the decoder.
If I have a picture, I have to keep the picture as the same as before if I encoded bits there. So it's basically limited by how much I can reconstruct the picture.
So if you don't have an attacker, your limitations are because you have a distortion constraint for the encoder. Okay, and the more severe this constraint is, the more limited you'll be in your communication performance.
Right. Haytham?
Two types of applications. In one of them, you want to embed data of different types, for example, sound in a JPEG image,
yes.
while introducing the sound information in the bits of the image. In another application, for example, in rights, in property rights, you would want the two data types to be the same. For example, either visual or both sounds, so that we don't want a scanned version of the image to lose all the data in it.
Right.
Is there a conceptual difference for both approaches?
Yeah, not here, because when I was talking about messages, I omitted to say that they're uniformly distributed over the message set. So what I'm assuming implicitly is that whatever your actual information was that you wanted to embed, you've converted that to a message that is uniformly distributed. So I've completely bypassed any source coding aspect. And at the end, I have bits that I want to embed, and I don't care what these bits are, whether they came from sound or from images or text. My assumption here is that I have a number of messages. They all have the same prior probability.
Any other questions? I have a question. How do these results sort of scale when you're applying them, for instance, let's say for 3D models, for instance?
Yeah, so here there's no notion of dimensionality of the signal. The only thing that mattered was the, for the length, the number of data, and then, I didn't speak much about that, but the distribution of the data. So I've assumed the ID for simplicity, and then at the end we saw, by taking a transform, that we map them into a new set. So whether the data are 1D, 2D, or 3D, it will be the same notion that you want a transform to have approximately independent components, and then you can apply the theory.
And there's no limitation?
Conceptually, no. I mean, so long as I can have independent components and say a parallel Gaussian model, then I can apply the theory.
Okay. All right. Yeah.
You mentioned that if you have a certain number of bits and you want to embed them, and the implication being the bits are themselves independent message bits.
Yes.
I was just thinking about the case of either voice or even video where the message itself is perhaps a Markov process.
Yes.
Does that help you? Or does it make it worse?
I would decouple. So I would take your Markov process. We really need a finite number of messages. So we would somehow need to convert that into independent messages, okay, for the theory to apply. Yes, yes. So in a sense, it's a problem that's really fairly independent of my embedding problem.
It needs to be come independently.
Yes, yes, yes. Incidentally, no, this is an interesting question. Recently, there's been a line of work. What happens if the message is correlated with the host? Okay, so that's another line of work.
How does the steganography scale with dimensionality? In other words, if we start off with something like a 1D signal, which
Right.
is speech, and then you start going to images, and then you start going to color images,
Yes,
and
yeah.
hyperspectral images, and then combining
Right.
all the things together.
Yeah, my view is that it's not so much the dimensionality that matters in answering that question. It's the complexity of the distributions, and where I've made some pretty optimistic comment here that steganography can be done. This is under idealized assumptions on sources that are really not met in practice. So if I look at, well, in fact, both audio and images, it's hard to come up with a model that is accurate enough that I can say I can preserve it exactly. I mean, if I try to preserve it exactly, anyway, it was not the correct model. It was only approximately correct. So this, my view, is the limitation, that we do not know exactly what are the statistics of the sources. We don't have a universal model, more so than the dimensionality issue. But I don't know if that makes sense. Okay.
All right.
One last question. Kind of where did you get those Chinese characters?
Yeah, my Chinese former graduate student did them for me.
Oh, okay.
We actually went back to many iterations because I asked her, can you prepare a little joke? And her sense of humor is different from mine, so I had to go through several iterations. She did a Garfield joke first, and I didn't like it. And so finally we did a nerd joke.